Hello there. This time my topic is uniform circular motion. First of all, I'm going to tell you what is circular motion. If a body which is moving in a circular path, then it's called circular motion. So we have so many examples, starting from a fan and planets revolving around the sun. And I've got a beautiful ball over here which is tied up with a string. And if I make this ball to rotate in a circular path, it's going to be circular motion. It's like I can just demonstrate and I can just make it to see. Just see this. It's going in a circular path. Now, the thing is, the question is, when can you say that the circular motion is very uniform? You can say that a circular motion is uniform when it travels with a constant speed. If the body travels with a constant speed, or it covers the equal distance in equal interval of time, then I can say that the motion, circular motion, is uniform. So that special case I'm going to discuss. What I have is, I have a body which is moving in a circular path of the constant radius. At some time, the body is at this point P, and it is called radial vector, which is actually drawn from the origin to the point P. That is actually our vector. After some time t1, or maybe after some time t, the body is at point P dash. So the radial vector is r dash. So I've got a body which is moving in a circular path and which is at constant speed. I have to be very, very particular about the term called is constant speed. I'm not saying it's a constant velocity. Velocity, of course, changes every time. So when the body is at this point, the velocity direction is this way. I have to draw a tangent to the point where I can just represent the direction of velocity. So speed of the body at every point in the circular path is constant, but not velocity. That's why this is called uniform circular path. So however, I have a body which is moving in a circular path with a constant speed at point P. The radial vector is r vector, and after some time t, the body which goes to the point P dash with the radial vector r dash. Now I would find out what is the displacement of the particle from P to P dash. I know that displacement is nothing but the shortest distance between 2 points. Now 2 points, one is P and P dash. So the shortest distance between P and P dash is nothing but delta r, which is nothing but a straight. So let me say delta theta is an angle which is made by radial vector for the two different positions, P and P dash. Now I'm going to define what is average acceleration from P to P dash. So that's what I'm going to define here. So average acceleration, I'm not going to mention any direction for the time being. I will do it later. But however, I'm going to tell what exactly the magnitude of the acceleration when the body is in circular path of the constant radius. So now average acceleration is defined as a change in velocity, delta v, by changing time. So overall change in velocity for the two different points, one is P, another one is P dash, and also the change in time. So maybe T1 for the first point P, after some time T2, maybe the first point P dash, the change in time is T2 minus T1, which is taken as delta T. So let me name this equation number 1. That's fine. Good, nice. Now, to measure the direction of the velocity, what I've done is I've drawn a tangent to the point P. So this tangent represents the direction of velocity. And here, if I want to know what's the direction of the velocity at this point P dash, I have to draw a tangent. The tangent represents the direction of velocity, that is V dash for R dash vector, or it is called radial vector. So at any point, if I want to know what is the direction of the velocity, what I have to do is I have to draw a tangent to the point. The tangent itself represents the direction of velocity. However, delta theta is the angle between R dash and R. Now, I'm going to do something. This V vector, here it is, V dash vector is acting from the same point, and I'm going to make use of the triangular law of vector addition. That is not, this is in same order and this is in a reverse order. So that I mean to say that V vector plus delta V vector is equal to V vector, because this is in reverse order, these two are in the same order. But I want what is delta V, there is a change in velocity, is equal to V vector dash minus V vector. This is just by triangular law of vector addition. That's not a problem here. But however, I just know that the magnitude of the velocity at any point is constant, which is because it's a speed which is actually constant. It's not a thing. However, the magnitude of the radial vector r vector, magnitude of r vector dash is also a constant, which is nothing but the radius of the circular path. Even it works for the velocity also. V vector dash with v vector is equal to speed of the body, which is also constant. Now, what I'm going to do is I have got two triangles. I've got V by drawing a tangent to the point P because of this R. I've got V dash by drawing the tangent to the point P dash because of R dash. So what I would say is I have got delta theta, which is angle between R vector and R vector dash. Also I've got delta theta, which is angle between V and V vector dash, because I've got V and V vector dash from R and R vector dash. So that's why I've got these two similar triangles, isosceles triangles. So I'm going to have OPP dash triangle, and also this triangle is MQN, which are of course isosceles similar triangles. So this is actually base length, this is side length, this is base length, this is side length. Of course, since I have two similar triangles, what I'm going to do is I'm going to take the ratio of the base length to the side length. So whatever the ratio of the base length to the side length in this triangle, which is absolutely exactly equal to this base length to the side length, that's what I'm going to do it. So however, I'm going to take the magnitude because I'm just measuring the distance here. So ratio of the side, base length is delta R dividing by, ratio is actually this delta R by, this is side length, that is R vector. There is a magnitude I'm going to take because I want to measure the distance. This by this in this triangle is equal to this by this in another triangle, which is because these two triangles are similar. This is by V vector. That's what I've got. I want to get a present expression for delta V. So that's what I'm going to write for delta V vector, which is equal to, however, I want the magnitude, that's why I'm not writing an error mark, which is equal to this V by R, that is delta R. This means, let me say this is equation number 2. Now what I would do is, I would define instantaneous acceleration. Of course, this average acceleration is defined for two different points, P and P dash, but the changing time interval is delta T. If I just make this delta T times to 0, that means the changing time interval changing to 0, what I can define is instantaneous acceleration. So that is defined as instantaneous acceleration, which is the limit delta T tends to 0, delta V by delta T. So what this average acceleration for delta T, that is change in time, tending to 0, then I can say that it's acceleration at certain particular time interval. What I can do is equal to limit delta T tends to 0. This delta V I have got from equation 2. I can just substitute V by R, delta R dividing by delta T. Since I'm talking, it's uniform circular motion. That means the speed of the body is constant. So that means the speed, that's V, is actually a magnitude of velocity, which is constant, which is independent of the time. It doesn't matter why the body is moving. It's independent of the time, and even the radius. Radius is also constant. It doesn't change with the time. I meant to say this V by R is a ratio which is actually independent of the time. So I can just take it out. V by R. I just apply this delta T tends to 0. There's a limiting value of time, delta R by delta T. This is nothing but again a speed. This is actually average speed. When delta T tends to 0, changing time interval tending to 0, this refers as instantaneous speed. And if I got again V by R, this term is taken as V, so V again. Got V, that's I got V squared by R. So what I've got is, I got instantaneous acceleration for the circular motion, which is nothing but centripetal acceleration. So what I've got is, I've got the expression for centripetal acceleration, which is nothing but instantaneous acceleration, which is just derived. I'll just talk about what is centripetal acceleration soon, which is equal to V squared by R. Where v is the speed of the body, which is moving in a circular path, and r is the radius of the circular body. Now, how would I increase the centripetal acceleration? By increasing the speed. If I decrease the radius, of course I can do that. However, by increasing the speed of the body, I can just increase the acceleration, which is the body which is moving in a circular path. The acceleration is increased by increasing the speed. That's fine. I know the relation between angular speed omega and the linear speed v by v is equal to omega r. So r is the radius of the circular path, omega is a angular speed, v is a linear speed. So I could write the centripetal acceleration in terms of angular speed by substituting for v as omega r whole square by r, that is omega square r square by r, I left with r. So centripetal acceleration in terms of angular speed omega, that is omega square r. However, I know omega angular speed is equal to 2 pi by time period, also is equal to 2 pi frequency. Frequency is number of rotations, a number of revolution in 1 second. On this time period, what is the time taken for one full complete revolution? That is what it does mean. So I can write centripetal acceleration in terms of the frequency. So omega is 2 pi f. So 2 pi f whole square times r. So 4 pi square f square times r. So the centripetal acceleration. So if the body just rotates in a circular path, if the number of rotations per second is more and more, the centripetal acceleration, which body gets, is more, because it's directly proportional to the frequency. That's nice. Now, I have to tell you what is the direction of the centripetal acceleration. That's more important. Before that, I have to find out what is the direction of this resultant velocity, because if I got v and v dash, I've got v dash here, this is y. So this resultant delta v, which is perpendicular to the displacement delta r, and also which is always directed towards the center of the circular path. So what I've got is r, which is a radial vector, and this is v, which is a velocity, which is I've got from tangent, which is drawn at the point P. I know that this r, that is radial vector, and the velocity both are in perpendicular direction, that means 90-degree angle. And even for r dash and v dash. So the resultant displacement and the average velocity, or its a resultant velocity, also perpendicular to each other, which is always directed towards the center. Now, the direction of the centripetal acceleration is always perpendicular to the displacement, and also which is always directed towards the center of the circle. No matter where is the point, maybe somewhere here, draw the tangent, that will be the velocity direction. But at this point, if you want to know what is the direction of the centripetal acceleration, you have to draw a line which is towards the center. That's itself, it is the direction of centripetal acceleration. So no matter where the body is, the direction of the centripetal acceleration is always directed towards the center. That's fine. Now, if I want to define what is a force, centripetal force, I've got a term for centripetal acceleration. Centripetal force is equal to mass into centripetal acceleration. That's no change. So mass into centripetal acceleration term is here, v square by its square, which is very, very, very famous equation for the centripetal acceleration. So which is mass times speed square dividing by the radius of the circular path. Of course, it's understood that if the body is moving at a greater and greater speed, the body has to get more and more centripetal force. So now the question comes, if I have a ball which is tied up with a wire, my question is, if I just make this ball to rotate in a circular path, of course I have to pull it every time because I have got a support over here. So I will do it. So this is actually a circular path, isn't it? This is moving in a circular path with a constant speed. A question comes, what makes this ball to be in a circular path? We can say, okay, there's a string. But what provides what is a necessary acceleration? What provides this ball to get the necessary acceleration? What provides this ball to get the centripetal force? That is nothing but a string, and where you have the term called tension. There is something called a force, that is in terms of tension I define, which is mass of this ball times gravitational acceleration, which is nothing but 9.8. So there is a tension acting on the string which is responsible for this ball to move in a circular path to provide a centripetal acceleration and also hence centripetal force. Now, I will tell you something here. I told you that if you draw the tangent to that point P, you will get the velocity direction. That's fine. I already told that if you draw anywhere changing to the circular path, the tangent direction represents the direction of the velocity. That's what I told you so far. I would make you to believe this by showing a demonstration. So this is just a ball which is moving in a circular path. It has to move in a circular path. If I make it move, if I give some pull, and when I drop this ball anytime, probably somewhere here, if I just drop it, it has to go in the direction of the tangent. If I drop somewhere here, it has to go in the direction of tangent. If I drop somewhere here, everywhere, if I just drop it, it has to go in the direction of the tangent. That's what I'm going to show. So I'm going to revolve this ball in a circular path, and that is actually nothing but uniform circular motion. Just want to drop somewhere. If I just break the string, that means I just do not provide any force. There is a tension force. What happens? I'm going to show you now. I expect, because of this derivation, I got something, and I've got something like V, which is actually in the direction of the tangent. So if I just cut the string, it has to move in the direction of the velocity. I'm going to show you now. So this is the mass, this is the radius of the circular path. I'm going to move it. So if I just, what I will do is, if I just drop over here, it has to move in this direction. If I drop over here, it has to move in this direction. So I don't know where I'm going to drop, but you have to observe it. If I drop any point, it has to move in the direction of the tangent. So at that point, I have to draw the tangent. In that point, it doesn't go. So I'm going to do is, this is the final time here, I'm going to do it. I may drop over here. I think that I can drop over here. I will do it. So I just dropped here. I just broke the string, and it moved in the direction of the tangent. I told you, any point if you draw the tangent, that's the direction of the velocity. That's the direction of the motion of the ball. And thanks for watching my lecture. So hoping for your support. We'll see you in the next video.